The European People Group for Particle Research, CERN, is revealing nuances of another particle smasher today, something on different occasions greater and twice as significant. It has viewed 3 new particles that could help us with sorting out how our universe was imagined and what its future resembles. Scientists at CERN have, as of late, uncovered revelations that turn how we decipher the universe on its head. Beneath the outer layer of their weighty tests lies a vast expanse of particles and powers so weird they could be straight out of sight. From potential sections to various viewpoints, to particles that challenge the very basis of reality. What confounding secrets are hidden inside these tests? Could we bounce into the universe of CERN and unravel the pieces of knowledge that could reevaluate our universe? The entryway to new viewpoints, a wormhole, could theoretically appear out of nowhere overhead, and the clarification would be the notable assessments led at CERN, home of the gigantic Hadron Collider, LHC. The LHC is the world's greatest and generally strong particle smasher, tracked down near Geneva, riding the line between Switzerland and France. There are secrets about this bizarre affiliation that the world doesn't have some familiarity with, secrets that could, in fact, change how we view physics in the universe. CERN, the European Association for Nuclear Research, works this tremendous logical instrument. It stretches more than 27 kilometers and sits deep underground. The primary capacity of the immense Hadron Collider is to allow physicists to test the estimates of different hypotheses of particle material science. This incorporates the high-profile assessment of the standard model of atom physics, which helps us with sorting out the essential building blocks of the universe. At its center, the enormous Hadron Collider works by accelerating protons to practically the speed of light prior to crushing them together. These effects produce a shower of new particles, which specialists study to gain insights into the laws of nature. It was through such preliminaries that the Higgs boson, often referred to as the God particle, was viewed as in 2012. This disclosure confirmed how particles acquire mass and was a huge moment in atomic physics. The tests led at the enormous Hadron Collider are critical for sorting out characteristics that occur under absurd conditions, practically identical to those not long after the Big Bang. The data accumulated can fill us in more about how the universe started, evolved, and about the fundamental constituents of matter. This makes the enormous Hadron Collider a player in possibly uncovering new parts of reality, angles that could make sense of insider facts surrounding dark matter and the fundamental forces of nature. Such high-level experimentation at CERN doesn't come without concerns. Some speculate about high-energy tests creating dark holes or exotic matter that could pose threats to Earth. However, CERN ensures that all safety measures are met and established. Specialists closely monitor these assessments, and studies and theoretical models assert that any dangerous circumstances are incredibly unlikely. Through its continuous assessment and disclosures, CERN helps us understand the universe better and shows the incredible capacity of human innovation and collaboration in pursuing knowledge. The LHC is humanity's current wonder. The colossal Hadron Collider at CERN isn't simply an incredible piece of technology. It is a marvel of modern science and engineering. Organized under the Swiss-French border, the colossal collider goes through a tunnel 27 kilometers in width and is as deep as 175 meters underground. This makes it the largest atom collider in the world and one of the primary instruments in the field of particle material science. The development of the enormous Hadron Collider is designed to handle assessments of remarkable scale. The chief ring of the collider, housed in a tunnel with a breadth of 3.8 m, contains 2 connecting parallel beam pipes. Each pipe coordinates protons in reverse directions, rapidly advancing them with a series of superconducting magnets. These magnets are fundamental for maintaining the path of the protons, bending their course at speeds close to that of light. Surrounding the beam pipes are layers of cooling systems that keep a temperature colder than space, required to keep the superconducting magnets at their intended working temperature. The size of the enormous Hadron Collider is also highlighted by its use of thousands of magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 meters long and weigh 35 tons each, showing the enormous physical scale and creative ambition behind the collider. The primary job of the enormous Hadron Collider is to examine the basics of the universe by seeing the tiniest parts of matter. By accelerating particles to practically the speed of light and then impacting them, the Colossal Hadron Collider allows physicists to study the resulting particles that are created during these collisions. This process helps in testing and expanding our understanding of the standard model of particle physics, which is the current best description of the subatomic world. One of the key objectives behind the enormous Hadron Collider's tests is to uncover the secrets of the Higgs boson. Its discovery at CERN in 2012 confirmed speculation about how particles gain mass. The Huge Hadron Collider also investigates other crucial particles and forces, looking to address fundamental questions like the presence of dark matter and the nature of the universe. Not long after the Big Bang, the gigantic Hadron Collider hopes to confirm the presence of new particles that speculative physics predicts but has not yet observed. These investigations are key for potentially finding new physics beyond the standard model, including supersymmetry and aspects beyond the normal three-dimensional perspectives. The vision behind the enormous Hadron Collider isn't simply to sort out the universe's structure, but to foster global collaboration, with thousands of researchers from over 100 nations participating. The enormous Hadron Collider is proof of worldwide support in the quest for knowledge. Its design and scale enable it to tackle the most serious questions in physics. Its inspiration extends beyond simple scientific interest, aiming to develop how we interpret the universe and inspire global collaboration in science. Through this gigantic and complex contraption, humanity continues to stretch the boundaries of what is known and venture into the quantum realm. But how does the enormous Hadron Collider really work? At the heart of CERN's research facilities, the enormous Hadron Collider serves as a powerful magnifying lens into the quantum realm, allowing scientists to see and study the critical particles that make up everything in the universe. The process of particle acceleration and collision at the enormous Hadron Collider is a key method for testing the underpinnings of physics. Inside the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel inside tubes kept at ultra-high vacuum, recreating the conditions of space. Superconducting electromagnets, chilled to temperatures colder than space, help steer and focus the beams at designated impact points along the tunnel. These beams collide, smashing particles together with gigantic energy. The collisions produce a collection of subatomic particles, some of which are extremely unstable and exist only for fractions of a second. To detect and investigate the outcomes of these collisions, the enormous Hadron Collider is equipped with large detectors, ATLAS, CMS, ALICE, and LHCb, each designed for specific types of analysis. These detectors capture data about the particles, including their mass, charge, and energy. This information helps physicists test predictions of particle physics theories, including the standard model, and investigate particles and forces that govern the universe. One of the most significant discoveries at the enormous Hadron Collider was the discovery of the Higgs boson in 2012. This particle, sometimes referred to as the God particle, is significant because it provides evidence for the Higgs field, which is responsible for giving mass to fundamental particles. The presence of the Higgs boson was predicted by the standard model, and its discovery was a fantastic achievement, confirming long-established theoretical predictions. Beyond the Higgs boson, the enormous Hadron Collider has also been instrumental in finding a range of other particles. For instance, the collider has provided evidence for the existence of pentaquarks and confirmed the presence of tetraquarks, particles composed of 4 and 5 quarks, respectively, particles that had never been observed before. These discoveries expand our understanding of hadronic matter, which is matter made of quarks bound together by the strong force, the force that holds atomic nuclei intact. These discoveries showcase the predictive power of the standard model and also open new avenues of exploration in particle physics, offering insights into the behavior of matter under extreme conditions, like those shortly after the Big Bang. Speculative risks, such as strangelets or miniature black holes, have been subjects of public interest and scientific investigation. Strangelets are a hypothetical form of matter that is more stable than ordinary matter. The theory suggests that strangelets could convert any matter they come into contact with into bizarre matter. The fear surrounding this theory is that, if strangelets were produced during particle collisions at the enormous Hadron Collider, they might trigger a catastrophic chain reaction, converting all matter on Earth into bizarre matter. However, Extensive research and safety assessments led by CERN and the global scientific community have addressed these concerns. Studies have shown that even if strangelets did exist and were produced at the enormous Hadron Collider, they would most likely be highly unstable and decay too quickly to cause any transformation of Earth's matter. Additionally, enormous cosmic rays, high-energy particles from space, constantly hit the Earth with energy levels much higher than those produced by the enormous Hadron Collider, without producing any strangelets. This normal assessment suggests that strangelets are not a credible threat. The concern that the enormous Hadron Collider could create small black hole stems from speculations about extra dimensions in physics. According to some theoretical models, high-energy collisions inside the LHC could produce tiny black holes that would evaporate instantly due to a process called Hawking radiation, named after physicist Stephen Hawking. Scientists agree that if miniature black holes were ever produced at the LHC, they would pose no risk. First, any such black holes would be small and temporary, dissipating before they could interact with surrounding matter. Second, the energies involved in LHC collisions, while large by human standards, are still far lower than the immense cosmic ray collisions that occur naturally. Since no dangerous miniature black holes have been observed from astronomical ray interactions, it is extremely unlikely that the LHC would produce any dangerous results. CERN, alongside independent boards, conducts careful security reviews to ensure that the experiments conducted at the LHC pose no threat to humanity or the planet. These reviews include theoretical analyses, test data, and safety protocols to address any potential risks. While the LHC's experiments continue to push the boundaries of how we interpret physics, they are conducted with a high degree of responsibility and scientific oversight. This ensures that humanity can benefit from groundbreaking discoveries without facing unnecessary risks. Speculative risks often sound more like science fiction than plausible scientific outcomes. The scientific consensus, based on extensive research and natural cosmic events, is that the experiments at the enormous Hadron Collider are safe, and the potential risks are minimal. One of the most interesting and unusual investigations proposed at CERN is the search for magnetic monopoles. A magnetic monopole is a hypothetical particle that is a magnet with only one magnetic pole, either a north pole or a south pole. In contrast, traditional magnets typically have both a north and south pole. The presence of magnetic monopoles was predicted by physicist Paul Dirac in 1931, who showed that their existence would explain why electric charge is quantized, meaning it comes in discrete amounts. Despite their theoretical importance, magnetic monopoles have never been seen at the colossal Hadron Collider. Researchers have been searching for evidence of these elusive particles. If magnetic monopoles were ever detected, they would revolutionize our understanding of magnetic fields and could lead to major breakthroughs in technology, including the development of new types of energy storage and transmission. Furthermore, the discovery of magnetic monopoles would provide experimental evidence for grand unified theories and string theories, which attempt to explain all fundamental forces of nature within a single framework. While the search for magnetic monopoles may seem elusive, it embodies the spirit of investigation and curiosity that drives scientific inquiry at CERN. The quest for such rare and potentially transformative particles reflects the organization's commitment to exploring the unknown and expanding the frontiers of human knowledge. Another remarkable experiment at the enormous Hadron Collider involves studying the possible presence of particles that could travel faster than the speed of light. According to Einstein's theory of relativity, the speed of light is the ultimate speed limit in the universe. However, some theoretical models propose that particles called tachyons could exist, which would always move faster than light. Detecting tachyons would fundamentally challenge our understanding of spacetime and causality. While most physicists remain skeptical about the existence of tachyons, the search for such particles at the enormous Hadron Collider demonstrates the facility's openness to exploring even the most speculative aspects of theoretical physics. The enormous Hadron Collider also enables scientists to conduct experiments that replicate conditions of the early universe, shortly after the Big Bang. These high-energy collisions create a state of matter known as quark-gluon plasma, which existed only moments after the Big Bang. By studying this plasma, physicists hope to better understand how the universe evolved from its initial high-energy state into the complex and organized universe we observe today. In summary, these diverse experiments at CERN, from searching for magnetic monopoles to creating quark-gluon plasma, highlight the breadth and ambition of scientific investigation conducted at the Colossal Hadron Collider. They demonstrate how CERN is pushing the boundaries of what we know about the universe and exploring new areas of physics that were once thought to be purely speculative. The enormous Hadron Collider's ultimate goal is to push the frontiers of human knowledge, unraveling the secrets of the universe by smashing particles at extraordinary energies. It allows scientists to explore the fundamental nature of matter and the forces governing the universe. This vigorous quest for understanding mirrors humanity's intrinsic curiosity and desire to explore. The discoveries made at the enormous Hadron Collider have broad implications for our understanding of the universe. By testing the smallest building blocks of matter and the fundamental forces at play, these studies enhance our comprehension of the universe's origins, evolution, and ultimate fate. They offer insights into the very fabric of reality and help address some of the most profound questions about existence. Furthermore, the technological advancements and scientific breakthroughs emerging from enormous Hadron Collider research have practical applications beyond particle physics. The development of advanced detectors, processing systems, and data analysis techniques has contributed to progress in various fields, including medicine, materials science, and information technology. The enormous Hadron Collider also fosters global collaboration, inspiring a new generation of scientists and researchers worldwide. Working together, sharing knowledge and expertise, scientists unlock the universe's secrets. This international collaboration is a testament to the power of science to transcend boundaries and unite people in the pursuit of knowledge. In conclusion, the enormous Hadron Collider is a cornerstone of modern physics, enabling momentous discoveries and stretching the limits of what we know about the universe. Its experiments uncover the nature of fundamental particles, forces, and the origins of matter, offering invaluable insights into the secrets of existence. Through its technological innovations and global collaborations, the enormous Hadron Collider embodies the spirit of scientific inquiry and the vast potential of human curiosity. As we continue to explore the universe through the Colossal Hadron Collider, we move closer to answering some of the most critical questions about our universe and our place within it.